So I'm going to talk about some unusual effects that we expect should arise in a class of materials. And since this is a short talk, I'd like to begin with a one-slide summary of the work done mainly by Shauvik Kundu and Jai Pandey. They are the main authors of everything I'm talking about. So the one-slide summary is this. Uh, you know that when you have spin orbit coupling, the spin rotation invariance is not present in the magnetic interactions, but this can have many manifestations. You can have exchange anisotropy, so the exchange couplings between neighboring magnetic ions can be direction dependent in spin space, and you can also have single ion effects in spin 1 and higher ions, which are completely local sort of Hund's rule dominated effects of spin orbit coupling. And these two things have sort of different origins microscopically, which you can see, for example, in tight binding descriptions of spin orbit coupled Mott insulators. There's some literature on that. And our message basically in this talk is that if these two kinds of effects compete with each other, so you have competing anisotropies, then the interplay of this competition and the underlying geometric frustration of the lattice, you're on a Kagome lattice or a pyrochlore lattice or some frustrated lattice, then the interplay of the frustration and this competition between two kinds of anisotropy can drive entirely new kinds of phases and transitions. And we find that quite exciting as theorists. But I should immediately say, caveat emptor, we don't know a candidate material, and maybe some search of the kind Umesh was talking about is needed to see what might be candidate materials. So let me start. I'm going to give you 3 examples of this, and since I've already given you the one slide summary, it doesn't matter how many of the examples I get through. So please stop me and ask questions if you have any. We don't have to get to the end of the talk. So let's take the first example of this effect that I have in mind, which is if you have a Kagome antiferromagnet with spin 1 ions now, and a very strong easy axis anisotropy in the exchange coupling. So the exchange coupling is predominantly among the Z components of the spins, but the single ion anisotropy is actually competing with this. So this term, if you think about it, likes the spins to be aligned in the Z direction. But the single ion anisotropy has a positive delta and a large positive delta. So it actually prefers the spins to lie in the plane. So in this sense, there's a competition between these two scales. And if they happen to be the largest scale in the problem, then you can have interesting physics. So in particular, the clean sort of case to consider, the example that I'm going to use to illustrate this point is to consider this very simple Hamiltonian. And to begin with, I'm just going to leave out the transverse exchange, although you can put it back in, and we've done that. And we are going to imagine a situation where Jz and delta are both large and comparable to each other. So they're the largest scale in the problem, but they're not exactly identical, of course. That would be too much fine tuning. So there's some difference between them. That difference is mu, right? So the small parameter in the problem is now mu divided by J and temperature, right? And J itself is very, very large. So that's the regime, that's the low temperature regime we want to think about. And if you think about this low temperature regime, and so we can ask what happens for various values of magnetic field. Now I'm going to imagine putting a field in the Z direction. So let's start with the example where I put a field that's large enough to get to the 1/3 magnetization plateau. So in these kinds of anisotropic Kagome magnets, you have 1/3 magnetization plateaus. And so there's a range of B which has a large width. You don't need to fine tune, B of order 2J. So you need a large magnetic field. That's the drawback of this first example. If you have a large magnetic field in such a regime, you're on the 1/3 magnetization plateau. So the way that plateau gets realized is each Kagome triangle has total spin Z of 1. Now the key point here is that in a spin 1 system, you can realize this in 2 ways. I mean, you can just draw pictures and see there's exactly two ways you can do this at the level of one triangle. You can have one spin pointing up and the other two in the Sz equal to 0 state, or two up and one down, right? These are the only 2 ways. And these two are not exactly degenerate. There's a small energy gap between them. That energy gap between them is order mu, which is small, but all other configurations are going to be very high in energy and basically not important for the low energy physics. So that's the setting. And this is the setting Shovik analyzed for his thesis last year. So if you think about this setting, it actually admits a very nice, simple geometric interpretation, which reminds us of some classic sort of StatMech problems. So this is the picture I'm trying to draw to explain that connection. So you can think of each SZ equal to -1 as a dimer on a link of the honeycomb lattice whose bonds pass through the Kagome sides. And you can think of each SZ equal to 0 as a segment of a loop. And the reason the SZ equal to 0 is form a segment of loops is that you always get them coming in, uh, pairs. So SZ equal to 0s form loops on the honeycomb lattice. SZ equal to -1s can be thought of as dimers. And what you've got is a fully packed arrangement of loops and dimers, so that every vertex of the honeycomb lattice, the graphene lattice, is touched by at least one dimer or has one loop passing through it. And the loops can be of various sizes, right? And whenever you have these sorts of fully packed configurations, you can think in terms of a divergence-free polarization field. This goes back to work on ferroelectrics in the 80s. So you can, for example, assign a polarization of 2/3 going from A to B when there's a dimer, and when there's a loop segment, polarizations of 1/6 going from A to B, and when it's empty, you have the polarization in the opposite direction. And the key point here is that when you make this mapping, this polarization field is divergence on the lattice. And so basically you've got a microscopic description in terms of a divergence free polarization field. And in 2D, of course, you can solve this condition by just writing P as curl of H, which is just a transverse derivative of a scalar. And if you think microscopically, what is the problem you have to solve in this low energy limit is a very simple statistical mechanics problem, which is a generalization of the dimer model. It's this fully packed dimer loop model where there's a weight W for every dimer. So that's the problem, right? And you can study it numerically. But before I show you numerical results, it's good to think about it a little. So let me just do that here. So some theoretical perspective. Every time you have one of these divergence-free polarization field kind of descriptions and a dual height model, you can think in terms of what to expect. And the simplest things in terms of symmetries is that you have sort of gapless behavior controlled by a grad phi square kind of action for this random surface whose height you're talking about. And this is known, for example, in the context of the W equal to 0 limit of our problem, which is the old problem of fully packed loops on the honeycomb lattice, well-known problem. It's also known in the limit of the fully packed dimer model, which is the W equal to infinity limit of what we are talking about. So in both limits, these are well-known sort of things. But here we have a physical situation where we are forced to interpolate between these two limits. So that's what makes it interesting. And this interpolation W, remember, is nothing but the fugacity of these dimers, which is nothing but, it's just the exponential of this small energy difference mu arising between delta and J, the two competing anisotropies. And we know the answer both at W equal to 0 and infinity. You have these power law distributions with dipolar correlations. That's old physics known from sort of ferroelectrics in 2D. And the question is, how do you interpolate? And the simplest thing you might expect is that you will just go continuously from one limit to the other. They're both the same kind of power law system, gapless behavior, not very different from each other. So some microscopic parameters will change, but nothing will happen. That is the naive expectation. And because it's always described by some height action like this. The only thing that's different between the two limits is that this height is actually an angle. So this is actually an XY model. And the periodicity in heights in the pure dimer limit is h going to h plus 1, but in all other cases, it's h going to h plus half. So you expect that the pure dimer limit is special, and all along the W axis, you just have a XY model with this redundancy, right? So that would be the naive expectation, and that's what we started out expecting. But we decided to just, for completeness, do the numerics and check. And we did the numerics using fairly straightforward standard methods with a little bit of a twist, which I won't go into here. But the key point here is that these methods allow us to measure the correlation function between two test charges. Now, by charges here, I mean violations of this divergence-free constraint. So remember, there's this divergence-free field. uh, divergence of P is 0, but you can violate it at two places with a plus half and a minus half divergence and look at the correlation function of these test charges. And that kind of measurement is easy to do in these methods. So we have that measurement. And then we also can measure the size of these loops formed by the Sz equal to 0. So that's a geometric characterization. And we have another sort of topological characterization in terms of the flux or the winding number of this polarization field. So we look at it in three different ways. And in all three ways, we seem to find something that violates this intuition I tried to present to you. We find a sharply defined phase transition between small w and large w. In terms of loops, you can think of it geometrically as a transition between short loops and long loops. So there's a phase in which the zeros make very long loops, system spanning loops, and there's a phase in which the zeros make very small loops. And there's a sharp transition around w equal to 2 on the square lattice, which is just a toy model we did to check our results. But really, this is the interesting system. And around 1.5, there's a transition. So that's the geometric picture for the transition. Okay, I don't know what the error is, but I think it's a bug in Acrobat. There's also this topological distinction, which is that this polarization field, if you put periodic boundary conditions, is just some winding around the torus, and in principle it can be any half integer. And we find that at this critical value of w, suddenly all half integer windings get excluded from the system. All half integer flux is expelled and you only have integer fluxes. So the flux gets confined. And that transition is very clear if you look at the probability distribution of the fluxes. It's Gaussian in both phases, but in one phase all half integers are allowed, and in another phase only the integers. So there's this very clear transition which we can measure by, which we can look at in a very sharp way by looking at the probability that you get a half integer flux, and that probability goes basically from 1 to 0, and there's a crossing at the critical point. So that's the second sort of topological characterization of the transition. And then there's this dynamical characterization having to do with the distance test vortices or test charges can move away from each other. So in the small w phase, two half integer charges can just move apart. They're sort of power law deconfined. But in the large w phase, they get confined. So you can see that here the correlation function between two half charges just decays exponentially very fast to 0 at large w, and at small w it's some power law. So it's power law deconfined. So there's these three ways in which we see this transition which we didn't expect. And what this transition is telling us is that at low temperatures in such magnets on the 1/3 magnetization plateau, there's two kinds of power law Coulomb liquid states of this magnetic system with the kind of topological transition between them. So that's the first example of what competing anisotropies can do. How am I doing on time?
14 and a half. So
very good. 5 more minutes before questions or 10 more minutes? 10 more. Very good. Okay. There is another signature of this transition, which is now a dynamical one in terms of the spin structure factor. So in these Kagome magnets, you can do inelastic neutron scattering or elastic neutron scattering and look at the spin flip part of the neutron scattering, the spin structure factor. And you can use that to deduce sort of weight at different Bragg peaks in the structure factor. And what happens is, so let me show you the picture first of the. So if you did this kind of spin flip component of the neutron scattering analysis, you would find that in the large W phase, you get these pinch points that are characteristic of Coulomb phases, but you would not see any other feature. All these pinch points are the standard things you would expect, but nothing else. But in the small W phase, you will also see these bright spots, which are power law Bragg peaks corresponding to power law order at 3 sublattice wavelength. So there's this qualitative distinction between the two structure factors in the form of these spots that you should be able to see in one phase but not the other. And that comes about because there is, in addition to these dipolar correlators, also a modulation of the 3 sublattice wave vector in the small w phase but not in the large w phase. So this is a real consequence in the magnetic system of the underlying sort of StatMech. So this is the first example. It's not the simplest example. It just happens to be the first example we thought of. The simpler example is actually the same system but in zero field. Now don't worry about putting a large field to go to the 1/3 magnetization plateau. Just ask what happens in zero field. Now you don't get any funny confinement transition between Coulomb liquids. You get something much simpler but already interesting. So now you see each Kagome triangle has to add up to Sz equal to 0, and there's again two ways to do this. One is that you can just have this completely dead phase where this term wins and everything is Sz equal to 0, right? That's like a Van Vleck paramagnet. Or you can have these kinds of triangles where you have one spin up, one spin down, and the other spin Sz equal to 0. And again, the energies are slightly different by an order mu term. And if you analyze the low temperature behavior of this, you will expect that at small w, this will dominate. So you'll just get a non-magnetic state. And at larger w, this should start dominating. And you should get the usual Coulomb liquid behavior. So there should be some onset transition of Coulomb liquid behavior. And the question is, what kind of onset transition is it? And if you think about it in terms of, again, this polarization field and height action, the immediate sort of guess is this will be like a superfluid insulator transition in 2 dimensions, Kostelis-Thouless transition. So we checked that, and there's ways of making this more precise, which is to say you can think of the polarization field as the current of a boson, and think of this partition sum that I was writing down as the link current representation of a bosonic system, and then going into the long loop phase from the short loop phase is like a superfluid insulator, Kostelis-Thouless transition. In one phase the bosons proliferate, in the others they don't. So the question is this really what happens? So we checked this and we found indeed, let me just cut to the chase, that if you think in terms of the analog of the superfluid stiffness in this case, which is the mean square value of this polarization flux in any direction, indeed we see some separatrix kind of behavior that's very characteristic of the superfluid stiffness. So this is the superfluid phase, and then it goes insulating. So the small w phase is the insulator, and then when you cross WC, you get into quote unquote the superfluid, but that superfluid is just nothing but your Coulomb liquid at zero field, right? So this is another interesting effect of these competing interactions. Let me now give you the same story in 3 dimensions, which is perhaps where it's most interesting. Thinking in terms of spin 1 pyrochlore magnets in zero field and spin 3/2 pyrochlore magnets in zero field. Again, it's the same kind of toy model we are looking at to illustrate the point, which is that you have a very strong easy axis exchange and roughly equally strong easy plane single ion anisotropy that compete with each other. And the question is, what does the competition do in this pyrochlore geometry? And it's the same sort of analysis in each case, so I won't bore you with those details. There's multiple ways for each tetrahedron to add up to Sz equal to 0. That's the key point, right? And they are separated in energy by small amounts of order mu. And so at low energies, the whole thing is a competition between different ways of satisfying the ice rule in these pyrochlore magnets, separated by small terms of order, right? And this competition between these energetic effects and entropic effects leads to interesting transitions. That's the idea in both of them. So again, there's a description in terms of a fluctuating polarization field. In this case, you would write the divergence free nature of this polarization field as a curl of a vector potential, and you will get an action that looks like Euclidean form of 3D electromagnets. Yes. And so let me now say what happens, what we expect will happen in spin 1. In spin 1, we would expect, by analogy to that Kagome result I showed you, first of all, a transition from this non-magnetic Van Vleck paramagnet kind of phase to a phase which is the usual Coulomb liquid, and that's this superfluid insulator transition that we see. But then there's a surprise, there's a second transition, and the second transition is again one of these flux confinement transitions. So you have a Coulomb liquid of the standard kind like holmium titanate, and then at larger values of W, which you can access by going to lower temperatures, you will get a transition to a flux confined Coulomb liquid, where the flux is now got to be even integers instead of any integer. So you get 2 topologically distinct Coulomb liquids separated by a kind of a Z2 confinement transition. And again, we can understand this in terms of this link current representation of bosons, And in the boson language, the second transition is really a transition between a 3D XY superfluid to a 3D XY nematic. And that's why it's sort of Z2, which is consistent with the gauge spin duality in 2 plus 1D. And so let me skip that and just say in 3D, in spin 3 halves on the pyrochlore lattice, we have a similar phenomenon. We have a flux confinement transition, but that flux confinement is now a Z3 confinement. So the Z3 part of this U1 flux gets confined. The flux is now only multiples of 3 in one phase and any integer in another phase. So again, you have two topologically distinct Coulomb liquids. If you looked at neutron scattering, you will not be able to tell them apart. But if you do some dynamical measurements, which can be indirectly done by some pump probe things, you will see that sort of violations of the tetrahedron rule, which are these elementary charges, have different dynamics in the two phases, right? And there's very nice parallel work by Shubhro and his group, along with Sitadi, which have looked at these dynamical effects in the spin 3 halves case. And with that, let me just stop. Thank you.
Thank you, Kedar. Questions? Yes.
Very interesting model. And one thing, suppose you think about this in one case, as a hardcore boson with up and spin down spin layer. And can you throw more light on the costless or
Right. Yeah, so in some sense, if you're thinking of the SZ equal to 0 as the absence of the boson, yeah, so that's why it's kind of a superfluid insulated transition. On the one side, you just have vacuum, on the other side, you have a superfluid. No, I think the up and the down together make up the world lines of the boson. So that's this link current representation. When the SZ is plus or minus 1, that's the world line of the boson.
So the distribution of the another term. Whatever.
Yeah.
Other questions? So, Kedar, I have a question. When you are seeing, trying to see this topological transition, is there any sense in which you see a gap closing, or you probably don't know of what? It's not very easy to figure out. But
Yeah. So,
for example, low temperature thermodynamics have a
so the low temperature thermodynamics actually has a signature, which is the standard signature of the dual spin model's phase transition. So it's either it's a Potts transition or it's Ising transition. But what you're asking is interesting. In some sense, if you want to think dynamically, the half charges, them getting confined is like an exponential decay in their correlation function. So that's like a charge opening, gas gap opening. Yeah, that is true.